Hello, my friends. This is again me, Sir K, and I'm going to talk about some high order thinking skills test questions. This time around, we'll be talking questions on the topic circular motion and rotational motion. Okay? Such questions like if the angular velocity of a rotating body is doubled at constant angular acceleration, how does the linear acceleration change? So this and several other similar questions where you will probably see a lot of misconceptions. All right, so I invite you to just sit down and relax, watch, listen, and be clarified. Before I begin with the first question, let us look at or have a review of the relationship between linear and angular quantities in kinematics, right? So these are the commonly used equations in doing problems on uniform motion as well as uniformly accelerated motion. And the angular equations, the counterparts in the angular uh, motion. All right, you also have here the relationship between linear and angular quantities such as delta d and delta theta. Okay, the angular displacement is related to the linear displacement or distance, and that is shown by this equation. Delta D is equal to delta theta multiplied by R. Similarly, the linear velocity or speed is also related to angular velocity or angular speed with this equation V equals omega R. And we also have what we call centripetal acceleration, which is a linear quantity, and it is related to the angular velocity in terms of the equation AC equals the square of omega times the radius r. And lastly, we have what we call tangential acceleration, okay, which is related to angular acceleration alpha. Again, the relationship between tangential acceleration and angular acceleration is in terms of the radius r. So these are the equations both for linear and angular quantities that we will be using as we go through the questions. Question number one. A body in uniform circular motion has blank. We need one or more answers. Letter A, constant velocity. Letter B, constant speed. Letter C, changing direction of acceleration. And letter D, changing magnitude of velocity. Which among these options, okay, will make that statement, all right, when uh, placed in the blank, it will make the statement correct, all right? So let's imagine that this is the circular path of a body in uniform circular motion, all right? So let's again consider a particle that is moving around in a counterclockwise direction, okay? And at that point, okay, the direction of its velocity that is linear, it's a linear velocity or linear speed, can be represented by a vector arrow pointing to the right, all right, to the right. The rule is we always describe the direction of the linear velocity as being tangent to that point. All right, tangent to the point, so it's a line. You can imagine a line that touches that point and no other points around the circle except that point there. We label it as tangential velocity. Right, tangential velocity, okay, to emphasize that it's always tangent to that point. Now, at this instant, the body is also being accelerated, all right? And the acceleration is known as, we call it centripetal acceleration. Okay, the word centripetal means that the direction of the acceleration is towards the center of the circle, all right? Since this particular tutorial focuses only on the kinematics of uniform circular motion, in other words, we are not going to talk about so much about the dynamics aspect of circular motion, but it is also worth mentioning at this point that for a body to be able to move in a circular path, there must be a net force. Okay, a net force that tends to make the body move in a circular path, and that net force, for example, at this particular instant, the net force is directed towards the center, hence it's also called centripetal force. Okay, so it is the centripetal force that is considered the net force exerted on the body. Okay, that's the reason why the acceleration is also directed towards the center according to Newton's second law. Now, what if the body has changed position? Supposing it's now in this new position. Okay, by the way, uh, we are considering that the body is moving in a counter-clockwise circular motion, as indicated by this big arrow or curved arrow. All right. What if the body is at that point? Okay. How do we describe the tangential velocity? Again, it must be directed tangent. All right. Tangent to that point, but because it is in a counterclockwise manner, at that instant, the direction of the tangential velocity, okay, is that way. All right. So if we have a geographic map, we call that direction as north. All right. We imagine that the circle is lying on the x-axis. What I mean is the plane of the circle lies along the x-plane. Right. So x-plane, not vertical. Okay, but horizontal plane. Okay, so just like in the first position, in the second position, right, the direction of the acceleration is also towards the center. Okay, that's the reason why it's called centripetal force or central acceleration. Now, um, later we will also be talking about another kind of acceleration that a body in circular motion can possibly have. All right, we call it tangential acceleration. But in here, since we assume that the circular motion is uniform, just exactly what do we mean by uniform circular motion? We are given the choices, all right? Before we reveal the answers, okay? I said answers because there is one or more possible answers. Now, how do we quantify or calculate the magnitude of that instantaneous velocity or instantaneous speed? We simply use the formula V is equal to 2 pi r divided by the period capital T. Okay. This 2 pi r refers to the circumference of the circle. All right, 2 pi r. And then capital T refers to the time for one complete revolution. The time it takes for this particular body to go around the circle and then comes back to its original initial position. the time taken is what we call period, denoted by capital T. How about the centripetal acceleration? How is it expressed? All right, the formula, of course, is A sub c, or centripetal acceleration, is equal to the square of the tangential velocity divided by the radius r. All right, so we emphasize that we're talking about tangential velocity. All right, and for the acceleration, we are talking about the centripetal or central acceleration. What is the relationship between these two quantities? All right, because at any given point, even if the magnitude of the velocity is constant or doesn't change, all right, but considering the whole revolution or the complete motion of the body in that circular path, there is always a change in direction of the velocity, right? If, for example, all right, if, for example, here the velocity is directed to the east, in the second position, it's now directed north, all right? Then, possibly, when it reaches here, that direction of the tangential velocity will be south, and so on and so forth. How about the acceleration? All right. In the first position, we say that the acceleration seems to be directed north, while in this new position, it is directed westward. All right. So, in answering our questions or in deciding if each of the options here is considered correct or not, all right. Letter A, which says constant velocity, uniform circular motion, okay, doesn't mean that the velocity is constant, because when you say velocity, it includes not only the magnitude of the velocity but the direction as well. And we just said that the direction of the velocity is always changing. All right, so letter A is out, and letter B is checked. Constant speed, that's correct. How about the direction of acceleration? All right, a proof to that is our illustration. At this point, the acceleration centripetal is directed north, but in another point around the path, like this one, it's directed westward. So it means that the direction of the acceleration, centripetal acceleration, is also changing. Okay? The magnitude of the velocity, which simply means the speed, okay, at any given point, is just the same as the speed, which is, we said, is constant. Therefore, letter B and letter D are contradicting. All right? The speed or magnitude of velocity is not changing, but it is constant. Therefore, that makes letter D also incorrect. Now, may I go back to what I was about to tell you? What is the connection or relation between tangential velocity and the acceleration AC? All right. Even if the speed, tangential speed or tangential velocity is constant, the fact that there is a changing direction, therefore we say that the body is accelerated. All right. Remember, when there is change in speed or change in magnitude of the velocity or change in both magnitude and direction of velocity, we say that the body is accelerated. And the centripetal acceleration is the acceleration that is due to the change in the velocity. Take note, it is due to the change in the velocity of the body at any given point. It is not because of the change in the magnitude of the velocity, because we already emphasized that the magnitude of the instantaneous velocity or tangential velocity is always kept constant. All right? So that is how we analyze. And before we go to the next question, let us now reveal our answers. Correct answers are B and C. Question number 2. A ball tied to one end of a string is whirled in a counterclockwise direction along a vertical circular path. Consider the positions of the ball at points A, B, C, and D as shown in this illustration or figure. Question is, which of the following statements, okay, is or are correct? Again, this requires one or more answers. Okay, option letter A. It has the greatest speed at point C and the least speed at point A. Letter B. Its total acceleration, meaning the net acceleration, at any given point in the circle is directed to the center of the circle. For letter C, its total acceleration is due to the pull of gravity and the tension in the string. And option letter D, the net force or F net at point C, right, is upward, directed upward, and then downward at point A. All right, so we have to emphasize that we are not talking about a body that is moving along a vertical circular path. All right. Earlier in question number one, we were assuming that the body in situation number one was moving in a horizontal circular fashion, where it is possible to assume that the tangential velocity has a constant magnitude. In other words, uh, we can use the term uniform circular motion. That was in situation number one. But in here, question number two, the ball tied to one end of a string and then whirled in a counterclockwise direction as shown by this curved arrow, okay, along a vertical circular path. So, imagine that this circular path, all right, the plane of this circle is, uh, this is not lying on the x-axis, but it is lying on the y-axis, right? Hence, it's called vertical. That's the word uh, vertical that gives us this clue. All right. Now, consider the positions of the ball at points A, B, C. These are arbitrarily chosen points. Okay. Let's analyze further. All right. Where do we start? All right. According uh, to me, letter A is considered correct. All right. It has the greatest speed at point C and least speed at point A. Is that the only answer? Well, letter C is also correct. Its total acceleration is due to the pull of gravity and the tension in the string. All right. So I did not check letter B. That means B is not correct. But letter D is also given a check. That means letter D is also considered correct. Why? So let's begin by analyzing. Okay, so in analyzing the situation for question number 2, we have here the enlarged version of the illustration where we say that the ball is moving along a vertical circular motion, which is considered a non-uniform circular motion. All right. The direction of the circular motion is counterclockwise, and that is indicated by this curved arrow. Okay, I have chosen just point A and point C. These are the two arbitrary points that we are going to analyze and compare, okay, what we can say about the different quantities. For example, the tangential velocity, the centripetal acceleration, and so on. Alright, so as shown in the diagram, we label our tangential velocity with small letter v. Right? At point A, it is directed tangent to that point. Alright? And the acceleration or centripetal acceleration, of course, is directed towards the center. Alright? In other points, such as point C, alright, the same thing is done for the tangential velocity. It's directed tangent to that point. And then the centripetal acceleration, AC, is also directed towards the center. Okay? Now, since in a non-uniform circular motion, the force of gravity is already affecting the motion of the body, alright? Aside from the force exerted by the tension of the rope or string, alright, there is the force of gravity that comes into the picture. Alright, so for example, we say that at point A, okay, the moving body has the slowest speed at that point. Okay, it has the minimum or slowest speed, tangential speed. Now, its centripetal acceleration is still acting on the body because we assume that the string is still uh, still being used to whirl the object in a vertical circle. So there is still the effect of the force of the string. We call that the centripetal force because it is the force that causes the body to accelerate towards the center of the circular path. Alright, now what about at other points? Okay, after point A, it goes around with an increasing, alright, tangential velocity. So we say that the object is speeding up. Okay, so as it passes point A and continues to move towards point C, okay, the speed or tangential speed of the body is increasing, and this is because of the effect of gravity. Alright, because of that, okay, there is what we call a tangential acceleration, symbolized here by A sub t. Okay, this tangential acceleration is the result of an increasing magnitude of the tangential velocity. Okay, it is due to the change in the tangential velocity. Alright, the centripetal acceleration, as we probably know, is that component of the acceleration that is directed towards the center, hence the word centripetal. Okay, what causes this centripetal acceleration? Alright, we know that uh, whenever there is an acceleration, there must be a net force responsible for the body to undergo such acceleration. And that is exactly what is happening here. Alright? It is the string pulling the ball towards the center, okay, that normally exerts the centripetal force. Alright? For example, at point A, since the string is still tied to the ball, and it's pulling the object, the ball, no, towards the center, it looks like the direction of the tension force from the string is downward, right? And since the weight of the body or the pull of gravity of the body is also downward, so we now have a combination of the two forces, right? The force of gravity or the weight of the object plus the pull of the tension of the string. Okay, and that net force is just the vector sum of the tension force and the force of gravity. Right? That constitutes what we call the acceleration towards the center or centripetal acceleration. Now, just after moving from point A, okay, with an increasing tangential velocity, and the rate of change in the tangential velocity is exactly what we call the tangential acceleration. It is due to the increase in the magnitude of the tangential velocity. All right? How fast does the tangential velocity increase per unit time? That's exactly what is meant by the tangential acceleration. Okay. And we can imagine for as long as the force of gravity, okay, is not changing, for as long as the force of gravity is constant, then we can say that the tangential acceleration must also be constant. Okay. But because the acceleration towards the center or the centripetal acceleration is not constant, okay, according to the equation a sub c is equal to v squared over r, all right, where v is the tangential velocity at constant radius. If the tangential velocity is increased, okay, the centripetal acceleration will also increase, so they are directly proportional, all right? And since the tangential velocity is increasing, okay, from point A to point C, then it follows that the centripetal acceleration is also increasing. All right? Now, these two components of the acceleration, the tangential acceleration, which is perpendicular to the centripetal acceleration, when added vectorially, because they are perpendicular, we can add them by simply using the Pythagorean formula. Okay? And the resultant of the two components of acceleration is what we call the actual acceleration, labeled here as A and represented by the red arrow. All right? So if the centripetal acceleration is always towards the center, while the tangential acceleration is tangent to that point, the actual acceleration, okay, is directed in such a way that, okay, uh, for example, at this point, and we want to describe the actual direction of the acceleration, then we can use a trigonometric function, all right? A trigonometric function that will define a certain angle. Okay, but as you notice, when the body is at this point in particular, all right, such acceleration or net acceleration has also changed, not only in magnitude but as well as in direction. All right. So from point A to point C, it looks like the net acceleration is not pointing to the center of the circle, right? It is because the tangential velocity is always tangent and perpendicular, or tangent to the point but perpendicular to the centripetal acceleration. All right. So that explains why the actual acceleration from point A to point C is not directed to the center, and that happens because of the way the tangential velocity changes. It is increasing, all right? It is increasing, and therefore uh, we have what we call tangential acceleration that is always tangent to that point. Okay? And since the centripetal acceleration changes with uh, the tangential velocity, therefore it follows that the actual acceleration is also increasing from point A to point C. What happens when the body is already at point C? Alright. At point C, the body acquires the greatest, what we call tangential velocity. It is the fastest, or it has the fastest speed, tangential speed or velocity at point C. Alright? And it also has the maximum amount of centripetal acceleration, or AC, is greatest at point C. Okay? There is no more what we call tangential acceleration. Okay? No instantaneous tangential acceleration at point A. Simply because, by definition, since tangential implies that the acceleration is tangent to that point. Alright? And the force of gravity is directed downward. So, it doesn't make sense, okay, to uh, to say that there is an associated uh, tangential acceleration at point C, because in the first place it is the force of gravity that is supposed to cause a body to have what we call a changing tangential velocity, in which case from point A to point C, the velocity and the tangential acceleration are in the same direction. So we say that the uh, tangential acceleration is positive because it has the same direction as the tangential velocity. Now, what about after passing through point C? As it starts to go up, okay, to point A, because again of the pull of gravity, then what happens is the tangential velocity starts to decrease. All right? There is now what we call a slowing down circular motion. But then again, because of the decrease in the magnitude of the tangential velocity, okay, there is a tangential acceleration that arises at any particular point. This time, the direction of the tangential acceleration is opposite to the instantaneous direction of the tangential velocity. And we can see therefore that from point C up to point A, that tangential acceleration is negative. All right. So we can therefore um, come up with a summary of the important concepts for non-uniform circular motion. All right. How do we describe the motion of a body undergoing non-uniform circular motion, such as a ball that is being whirled, okay, an object that is tied to a string and then whirled along a circular or vertical circular path. That's an example. Another example is the motion of a roller coaster car. All right. So when the car of a roller coaster uh, moves around the loop, there are certain parts of the whole roller coaster uh, path where the loop is exactly vertical. All right, and therefore it's like analyzing this particular illustration. All right, now what can you say back again about the net force that's acting on the body, specifically at point A and at point C? Okay, so we say that at point A, the net force, all right, the net force acting on the body is composed of the pull of the tension of the rope or string and the pull of gravity. So we have here the equation for the net force T1 as the pull of the rope, okay, towards the center, plus the force of gravity, which also happens to be downward in the same direction as the tension. And when we equate this to the formula for centripetal force, mv squared over r, all right, we have now this formula that describes, okay, the relationship between the tension of the string, the force of gravity, and the tangential velocity of the body, which we said is considered the lowest, all right, speed or the minimum speed of a body moving in vertical circular motion. Okay, we'll come back to that after we also describe the net force at point C. So, at point C, the net force this time, since the force of gravity is opposite to the tension force, all right, to get their vector sum, we simply subtract tension T2, which is directed upward, and then minus the force of gravity or mg, which is directed downward. But then again, we equate it to mv squared over r. But the velocity that we use here, all right, is the maximum tangential velocity possible. So we label the difference between the v in our first equation for the net force as differentiated for the tangential velocity we are talking about in equation referring to point C. It is the maximum tangential velocity that we are describing here, whereas at point A, it is the minimum tangential velocity that has to be squared. Okay, now, uh, is there a possibility for the force of the string, okay, to become zero? And what will be the effect of that? All right. If you have experience um, doing this sort of experiment, all right, where you tie the object like a ball to one end of a string and then start whirling it in a vertical circular path, uh, you must have noticed that there is a possibility for the string to slacken or to get loose, especially when it reaches point A. All right. So if at point A the string is seemingly not pulling the object towards center, okay, we can assume that the force of the tension of the string becomes zero. All right. So at point A, if the tension is zero, then the net force acting on the body will simply be the force of gravity mg, all right, and that's equated again to mv minimum squared over r. That's what's going to happen the moment the string uh, is no longer acting on the body. All right. What is the consequence of that? The body, therefore, will have a certain speed. We call it v minimum. All right. Below this value of the v minimum, the object will no longer be able to move perfectly along this circular path. All right. Because there's no more tension coming from the string in the first place, all right, to provide the needed centripetal force, okay, on the body. And so therefore, it will be simply relying on the pull of gravity, mg, all right? So, whatever happens to the body now, without the effect of the tension, okay, it all depends on at what particular point is the pull of the tension totally disappears. All right. But because of inertia, okay, because of inertia, for example, at point A, if there is no more net force towards the center, okay, what happens to the body is simply to follow a straight line according to Newton's first law, isn't it? But because there is force of gravity, okay, we cannot expect that the object will continue along that straight path, all right, to the left. But instead, it will still be affected by the pull of gravity, and then eventually it just fall down, all right, but not along the exact circular path anymore. So, what's special about this V minimum? Okay, if you're going to derive for that, you will notice in the equation the mass m cancels out, and we have G equals V minimum squared divided by the radius. Okay, isolating for the V minimum, we get an equation for V minimum, okay, equals square root of Rg. But we label it as V sub c, meaning the critical velocity, tangential velocity. Critical in the sense that if the body in a non-uniform circular motion, okay, acquires a speed, especially at the topmost, okay, point in its circular path, all right, if the speed of the body, actual speed, tangential speed, is lower than that critical value, then we say that the body will be not, it will not be following a perfect circular path anymore. Okay, so what does that mean? For example, for any satellite that's orbiting the Earth, okay, that particular satellite should have a critical velocity in order for it to move perfectly around its orbit, okay, without falling back to the Earth. There is a critical amount of velocity that has to be maintained as much as possible. The actual velocity should be greater than that critical, all right, because if it becomes lower, then the body will no longer be able to move along a circular path. In the case of the satellite, we can imagine that the satellite, because of the pull of gravity, okay, there's a possibility that that satellite, okay, will just fall back into the Earth's surface, okay, into the ocean, probably, or into a uh, place where there are people, and that could be very disastrous. Okay, so that's how we analyze question number 2. All right, we were able to answer already the question earlier. We just tried to provide explanations as to why we have those answers. So we will now proceed to the next question. All right, in this question number 3, we have, or as shown in the figure, we have the top view of the path taken by a particle, all right, as it moves from point A, okay, to point B, and then to point C with constant speed. Okay, take note, with constant speed. Now, question is, which entry in the table here gives the correct geographic direction of the velocity and acceleration of the particle at point B? All right, here is point B again. We can imagine the particle moving at constant speed. All right, so when it's about to change direction, all right, initially it's moving south, then it's going to turn east, all right, exactly at that point represented by point B. How would you describe the velocity instantaneous? And the instantaneous acceleration as well. So you're given these choices A, B, C, and D. Velocity and acceleration. Okay, so we have here, of course, the geographic uh, symbol, direction, north, south, east, west. All right, so what do you think is the key concept, okay, being applied here? Well, we can imagine that the motion of the particle, especially when it is about to turn, all right, when it's about to turn uh, around this bend, all right, it seems to follow what we call a curvilinear path. So, in a way, it is undergoing what we call a curvilinear motion, whose center of curvature, all right, you can imagine the circle, something like that. So, if the object is exactly here, all right, where is the uh, imaginary center of curvature of this arc? All right, must be somewhere there. All right. In other words, northeast, somewhere in the northeast direction relative to the observer. So therefore, if it is at that point and the center of the imaginary circle is here, northeast, all right, northeast. There's no definite angle given, but we are sure it's between north and east. All right. Which between the two quantities, is it the velocity or the acceleration that should be directed towards northeast? All right. It is, of course, the acceleration. All right. For the body to be able to maneuver, all right, to maneuver a left turn. This is a car. The car has to bend, has to move around this bend and turn. Okay. Originally going south, then it's going east. There must be a centripetal force, okay, that should be acting on the particle in order to allow it to move in a circular, almost circular path. Okay? And we said that the direction of the F net and the direction of the acceleration, centripetal acceleration, that is, okay, are the same. Alright? So if the net force is towards northeast, then it follows that the acceleration should also be northeast. But there are two entries here which says northeast, northeast. Therefore, we have to describe the direction of the instantaneous velocity as well. So if there is an instantaneous centripetal acceleration, perpendicular to that centripetal acceleration, of course, is the tangential velocity. All right? So the tangential velocity is pointing towards something like between south and east, or we call that southeast. So therefore, the correct answer is letter D. All right? So this is not a very difficult question after all. For question number 4, which reads, for uniform circular motion with a given radius, which statement below is true if the period is halved? All right? So period, capital T, refers to the total time it takes for a body in, in circular motion to complete one revolution. All right? So our formula for, it says already there the correct answer is letter C. But why? Why is letter C the correct answer? Okay, recall that the formula for tangential velocity is 2 pi times r divided by the period capital T. Okay? So, in the problem, it is the period that you're going to change. You're going to divide it by 2 or halve. So, in the formula, if capital T is halved, then what is the effect of that to the tangential velocity? Okay? It's like 1 over 2, right? If 2 is halved, all right, if, if capital T is halved, then it means that you're going to, since capital T is in the denominator of 2 pi r, and then you're going to make it 1 or over 1 over 2, 1 half, right? Then we can make it like 2. B is equal to 2. In other words, uh, the effect of dividing the period by 2 is such that, all right, the effect is the velocity will double. All right, so letter C, B will be doubled, is correct. That's what's going to happen. But what about the centripetal acceleration? Will it be quadrupled, meaning will it increase 4 times its original? Let's check with our formula. For centripetal acceleration, okay, it's just equal to v squared over r, where v is the tangential speed. So again, since the speed is doubled, then you got to square it. Okay, doubling means it's 2 times the original, right? So what is the square of 2? Of course, it is 4. So the effect on the centripetal acceleration is to increase it 4 times the original, or using the word quadruple. That's the correct answer, letter C. Question number 5. All right. We have a particle that's moving in a vertical loop as shown in the diagram. And it has a varying speed. Okay. Just like a roller coaster car as shown in the figure, suppose that the particle experiences 4 times the acceleration at the bottom of the loop as it does at the top of the loop. Okay, compared to its speed at the top of the loop, its speed at the bottom of the loop is how many times as great? All right. So this is similar to what we earlier discussed. All right. Uh, it's all about a non-uniform vertical circular motion. All right. So I have here the choices, but let's go immediately to the explanation. All right. As shown in the diagram and as represented by the vector arrows here, since it's moving clockwise, all right, around this circular path, the tangential velocity v1 is to the right, and the acceleration, centripetal acceleration a1 is downward to the center. All right. Then at the bottom point, okay, we have the tangential velocity. The arrow is longer than the first tangential velocity v1, suggesting that at this point, indeed, the velocity, tangential velocity, is much greater than that v1. All right. And likewise, for the acceleration a2, the arrow is longer than the arrow presenting a1. All right. So this agrees with what we earlier discussed. But in order to answer the question, uh, it says that the particle experiences 4 times the acceleration at the bottom of the loop. Okay, 4 times the acceleration. So in other words, a2 is 4 times greater than a1. Okay, if that is the case, whereas to compare the speed at the bottom, all right, meaning referring to V2, okay, how is V2, or how many times is V2 greater than V1? All right, that is the meaning of the question. So what do we do? All right, we recall the formula for centripetal acceleration, which says AC is equal to V squared over R. All right, now if you're going to what do you call that, derive, okay, or isolate the formula for V, all right, it becomes V is equal to square root of AC times the radius R, right? Because it is the velocity that we want to uh, to determine, okay, as to what's going to happen to the velocity if the acceleration is changed, and the change, according to the question, 4 times the acceleration. So all you have to do is get the square root of 4, all right, assuming that the initial acceleration is 1 unit for constant radius, all right, just get the square root of 2 times 1, or I mean 4, square root of 4 times 1, and the square root of 4, of course, is 2. In other words, the effect on the tangential velocity is to make it twice as large. In other words, the answer to this question is letter B. So this is again a very relatively easy question. Okay, this question is now about rotational motion. When a sphere is rotating clockwise about its axis, which is perpendicular to the paper at constant angular velocity, okay, uh, which of the statements below would complete, okay, this statement? All right, we are expecting one or more answers. So it says in letter A, all right, all points within the sphere have the same angular velocity. Okay, the key word in the question is the term constant angular velocity. Okay, constant angular velocity meaning the angular or rotational velocity doesn't change both in magnitude and in direction. All right. So, and it is labeled with the, it's represented, denoted by the Greek letter omega, right? But let's first continue reading the options. In letter B, the angular acceleration of the sphere is said to be 0. For angular acceleration, our symbol is the Greek letter alpha. Letter C, the direction of the angular velocity is away from the reader or into the negative z-axis. And letter D, every particle in the sphere has 0 tangential acceleration. All right, so you may notice that uh, the some of the terms used here have already been identified, okay, with circular motion. So it looks like circular motion is quite similar in a way to rotational, to circular motion, rotational motion, all right? But what is the difference? Okay, I'm sure you know the difference between, for example, rotation of the Earth from the uh, other, what do you call this, motion of the Earth, what we call revolution. The Earth revolves around the Sun. At the same time, it rotates about its axis. So those are two examples. All right. The revolution of the Earth around the Sun illustrates circular motion, whereas the rotation of the Earth about its axis, all right, It's an example of rotational motion. So I leave it to you to figure out what's really the difference. Let's proceed to the explanation before I reveal the answer. All right, let's introduce, if you haven't yet encountered, okay, the formula for angular velocity. It says here, angular velocity omega is simply the amount of the change in angular displacement delta theta, all right, per unit time. So we're talking, in other words, we're talking about the rate of change, in the angular displacement, all right? How fast does a body rotate? That's exactly what we mean by angular velocity. And if you're talking about a sphere, a body that is spherical in shape, all right? Uh, if it is rotating about its axis in whatever manner, clockwise or counterclockwise, but according to this question, the axis is perpendicular to the paper. All right. So imagine that the axis is perpendicular to the paper if you are answering a test paper right now. But if you're looking at your screen of your computer, we imagine that the axis of rotation of this sphere is perpendicular to the screen. All right. And in our Cartesian coordinates, uh, we usually label upward and downward to mean the y-axis. The positive y-axis upward, negative y-axis downward. And to the right, we have positive x, and to the left, negative x. All right. Where is the z-axis? All right. That's exactly uh, what we mean here by the axis is perpendicular to the paper or to the screen of your computer. All right. Imagine a line perpendicular to the screen, or the axis may be either pointing towards you or away from you. All right. Towards the viewer or away from the viewer. Now, let's continue before we explain that further because it has something to do with letter C, option letter C. All right. So this is the meaning of angular velocity. If there is a change in angular displacement, all right, there is what we call angular velocity. Okay. And since angular velocity is also a vector quantity, it must have a definite direction. All right. Let's talk about that later. Let me show first what I have here. Another equation, very important equation, is the relationship between angular speed or velocity to linear speed or linear velocity v. And that is v is actually the original version of this equation should be v is equal to omega r. All right. But uh, we what do you call it, isolate omega and get this equation instead. Omega is equal to v over r. All right. So which means that the angular velocity or speed is just directly proportional to the linear velocity or speed if the radius is constant. All right. Now, imagine that each particle in the body of a sphere, all right, is a particle that is undergoing this rotational motion. Okay, it's not hard to imagine that each and every particle in that sphere, okay, once it starts to rotate, all other particles, okay, will also be rotating with the same angular speed or velocity, isn't it? All right. So that means letter A, all points within the sphere have the same angular velocity. We can consider that as correct. All right. But We'll have it checked later. All right, there. But I now have the complete list of my equations needed to explain these options. We also have angular acceleration denoted by Greek letter alpha. All right. When do you say that a rotating body has angular acceleration? According to the definition of alpha, it is equal to delta omega over delta t. It means that if that rotating body, okay, has a changing angular speed or angular velocity, okay, then therefore we say that it has an angular acceleration, right? Delta omega means change in angular velocity per unit time. That is the meaning of angular acceleration. If you recall, or I should say, have we encountered this formula for angular acceleration? I don't think. Oh, yes. This was presented in our first, what do you call that, slide earlier, right? In that particular table showing the similarities of angular and linear quantities, all right? That was given there. So alpha is said to be equal to tangential acceleration divided by the radius. That's how angular acceleration is related to a linear quantity, specifically tangential acceleration. Remember, a body has tangential acceleration when there is a change, either an increasing or decreasing tangential velocity. So it should follow that when there is a tangential acceleration, automatic, okay, it goes automatically that there is angular acceleration because now we are talking about a changing angular velocity. All right, that's the meaning of alpha, how it is related to tangential acceleration. All right, um, let me see. In letter B, the angular acceleration of the sphere is 0. Is this correct or not? Because according to the question, uh, the angular velocity is constant. There you go. The angular velocity is constant. So that means if the angular velocity is constant, therefore there is no angular acceleration. All right. Delta omega. There is no delta omega in this situation because it's constant. All right. The initial and the final omega are just equal. In short, alpha, angular acceleration, is 0. Therefore, letter B is correct. All right. How about letter C? The direction of the angular velocity is away from the reader or towards the negative z-axis. All right. I'll come back to that. Okay. Let's discuss first letter D. Every particle in the sphere has 0 tangential acceleration. We already said that. Okay, alpha is equal to tangential acceleration divided by r. So, it follows that if we isolate tangential acceleration, it becomes at equals alpha r, right? Tangential acceleration is just equal to alpha multiplied to r. And since we earlier already said that there is no angular acceleration, it is 0, then it follows that the each and every particle in the sphere has 0 tangential acceleration. All right? So, we accept letter D as a correct answer. But how about letter C? Is this correct? The direction of the angular velocity is away from the reader or negative z-axis. Okay. The answer is that is correct. All right? So, all of the options A, B, C, and D are correct. Let me now explain to you why letter C is correct. We have a rule in determining the direction of the angular velocity given the direction of what we call the rotational motion. Here it is. All right. According to the figure, in order for us to determine the direction of the vector omega along the z-axis, all right, we have to use what we call the right hand grip rule. All right. So we are looking at this side view. All right. As you can see, uh, the thumb is extended, making a right angle with the other fingers. All right. Before the other four fingers are curled. All right. Before you curl them, okay, you extend them first so that they make a 90-degree angle with your extended, or what do you call that? The thumb is positioned such that they form a right angle with the other four fingers. So, what you will do is you are going to curl the fingers, the other four fingers will be curled along the rotation. Okay, and if the rotation is counterclockwise, so you try to curl your other four fingers in counterclockwise manner, and then try to see where the thumb seems to point. All right. So we say that when the four fingers are curled in a counterclockwise manner, your thumb points in vector direction of rotation to the angular velocity omega. In other words, okay, the direction of the angular velocity must be towards the uh, what do you call this? Towards that direction denoted by the z-axis, right? The z-axis, uh, the z-axis. If, for example, in our earlier description of the z-axis that is directed into the what do you call that? Into the screen of your into the screen of your computer, all right? So if that is the direction of the thumb as you curl, as you curl your, as you curl your, let's follow this. The curling must be counterclockwise, right? But we will change the position of the axis. What we have here is the axis seems to be pointing north or upward, all right? Upward, okay? What if in the earlier example we had, all right? I forgot what number was that. Supposing the axis, okay, the axis of rotation is perpendicular to the screen, all right? And then you're going to follow the curling of your, what do you call this? Four fingers, okay? The four fingers will be curled counterclockwise, all right? So when you do that, the four fingers are curled counterclockwise. Where is your thumb pointing? Isn't it pointing towards you? Then you follow, right? It is towards you, right? Because the axis that I mentioned must be perpendicular to the paper. If you are uh, looking at a piece of paper on your desk, but if you are looking at the screen of your computer, imagine that there is an axis perpendicular to the screen. All right, and then you do your right hand grip rule. You try to grip that axis in a manner where you are going to curl the four fingers. All right, the four fingers will be curled in counterclockwise. All right, counterclockwise. Therefore, the thumb, your thumb, will be pointing towards you. All right, and that is actually the positive z axis. All right, the positive z-axis represents the direction of the angular velocity if the rotation is done in this manner. Okay, what we have here is that the axis of rotation is upward. All right, upward. Then you're going to hold or grip that axis such that your forefingers are curled counterclockwise. All right, look at that circular arrow. Counterclockwise, and therefore, where does your thumb point? It points towards the positive z-axis. Okay, so that is the meaning of, that is how we determine the direction of the angular velocity. Okay, you must have noticed that when we say direction of the angular velocity, we don't mean the direction of the rotation. They are two different quantities, all right? Clockwise and counterclockwise rotation is not the direction of the angular velocity, okay? But you use it in order to determine the direction of the angular velocity using the right hand grip rule. Before we end our discussion, let me just bring you back to the question we had earlier, okay? Uh, I was trying to explain to you why letter C, option letter C, is considered correct, okay? So, we actually uh, considered, all right, we considered all of them as correct answers, okay? Then, okay, I showed you the illustration on how to use the right hand grip rule, all right? So in that illustration, okay, the direction of the rotation was counterclockwise, and that's not the same as what's stated in the problem. Because if you look at the problem, we have the sphere that is rotating clockwise. All right. So um, noticing this earlier, I thought there was some kind of confusion. All right, because the question is telling us that the sphere is rotating clockwise, but in that illustration, to illustrate how the right hand grip rule, okay, is used, it was in fact referring to a counterclockwise rotation. So I expected that maybe some of you were quite confused. So I'm going to clarify that now. Why is letter C considered correct? Because if you're going to use your right hand grip rule, all right, you're going to follow the curling of your forefingers, okay, should follow the given uh, direction of the rotation, which according to the problem is clockwise, okay? So you try to curl your forefingers, and then the axis, all right, the axis should be pointing along your thumb, all right, along your thumb, which according to that illustration must also be directed perpendicular to the screen of your computer, all right? Or if you are looking at your test paper, for example, then you are describing the direction of the axis of rotation as if it is perpendicular, okay, to the paper, okay? Now, is it directed into the paper or away from the paper, okay? So that is what we would like to clarify, because in letter C, okay, what's stated here is the direction of the angular velocity is away from the reader. You are the reader, right? Is it really away from the reader? Okay, which also means into the negative z-axis, right? So once again, You curl your right fingers, all right? Try to grip the axis of rotation, but following the clockwise rotation, right? So isn't it that the thumb of your finger, all right, the thumb finger, I mean, all right, will be pointing into the plane of the paper, okay? And that is similar to when we say away from the reader, it's like saying into the paper or into the screen of your computer, okay? So this is specifically what describes the direction of the angular velocity when the rotation of the sphere is given as clockwise. All right? Since it's into the paper or into the screen of your computer, that is also commonly known as the negative z-axis. All right? The opposite of which, of course, is in into the reader or towards you, okay, which is the same as positive z-axis. So that is the explanation why we considered letter C as a correct option, right? So that would be all, and thank you again for your indulgence.